All right, so we're talking support vector machines continued. Everything just sounds so much cooler as soon as you throw in the word machine. Like this is going to be something something special. And we said, you know, if you've got let's say, you know, you got some dots over here, and then, you know, another class of dots over here. What we want to do, our goal is to find a boundary such that the maybe I'll draw a lighter line here, such that the margin is maximized, right? We're trying to maximize, bless you. You know, we want to maximize this margin here, okay, which we call gamma. Okay, so we're going to call this thing gamma. So we wish to maximize the margins of our boundary, okay? And then where we left off, okay, is you know, we left off something along the lines where, you know, we projected. Oh gosh, all right. You know, we wish to maximize the margins of our boundary. The margins of our boundary is the distance between the boundary and the nearest points to the boundary, right? So excuse me, are the distances from the boundary to the nearest points to the boundary. Okay, and we left off on Wednesday after projecting this, kind of saying that with you know, projecting 2 points, x1 and x2, onto the unit vector w over the unit vector that is perpendicular to the boundary. Okay, and then, you know, we established and we're going to, just for the sake of our thing, we're going to define kind of this distance between the nearest point and the boundary. This margin, okay, the margin's distance defined as gamma, okay, and with a little, you know, to do our solving, you know, defined as gamma, and with a little bit of math, we can say gamma is equal to 1 over w. Okay. And then we can optimize this using Lagrange multipliers. And I think I want to skip all of that math. There is an excellent lecture online where the professor in that lecture goes through pretty much the exact same steps that are displayed in the textbook, pages basically 187 to 189 in the textbook. He works through all of that, and it's MIT OpenCourseWare. Are you guys maybe familiar? Okay, great lecture. I'll link to it, and so recommended viewing. And it shows the steps to do our optimization. And basically, what it comes down to is that it just depends on the internal, the dot product of, or the inner product of our points xm and xn. Okay, so the results of the optimization, and it turns out that we don't have an analytic answer to the optimization. We have to kind of solve it numerically. Numerically being like things where you're using optim, right? Where you're not actually doing any kind of calculus and solving for the answer analytically, but you're plugging in a value, you try out another value, and then you keep going until you find a value where you can't find any more improvements, right? So that's like numeric optimization. We've kind of explored that a little bit, using our functions here. And the results of the optimization, do not depend on the W vector, but only on basically the inner product between pairs of points, okay? Inner or dot product of pairs of points. And basically what that's saying is that when you create your boundary, you might have and then the boundary ends up just being like this, okay? And it's really only, it's really only this point. The boundary is determined entirely by kind of these 3 points, okay? And it's determined by kind of like when we look at this, looking at across all the pairs of points, basically these pairs of points, when we look at these will have weights, okay, in our solution, and then everything else will be weighted to be 0, okay? So only these 3 points go into determining our boundary. Okay. And of course, in other problems you might have more than 3 points, but it's, these other ones, only these 3, I guess, red circled points, and then all of these other points, they, these are not used for boundary determination. Okay, these are also not used, and that's fine. But we have some side effects of this. Okay, this the way we've defined our optimization problem and the results that it's going to find. There are a few side effects. Okay, so this is the optimal result. For the way we have defined our problem. And the way we've defined the problem is that we're trying to maximize the margins, right? The side effect of this. Oh, okay. And then so these 3 points that go into determining the boundary, those 3 points, these are known as the support vectors. Okay, because we can always think of a point in our space as a vector, right? So we can say, this is a vector, and this is a vector, and this is a vector, and these are the support vectors. Okay, so the points that determine the boundary is known as our support vector. Is it okay that I skipped all the math for today's lecture? It would have taken the entire lecture to do it. So I do, of course you have all this free time, I know. But there's a very good solid, it's a 50-minute lecture showing the math for the support, getting to the optimization of the support vector machines. So if you're curious, you should watch. You should watch it anyway, but okay. All right, but some side effects. This is called the hard margin. So our current definition is called hard margin SVM. Okay, and we have some side effects. I don't know if we want to say this, it's a side effect, but it's because it's really, of course, this is what's going to happen, is that, we might have a data set where it looks kind of like this. All right, so of course, you're never going to get a classification problem like this, okay? All right, and if we do this, the margin would go right there down the middle, and that would be perfect, right? But let's say, this guy comes out here, okay? And now what happens is that the way we've defined our problem, now our margin has to try to accommodate this, and this is what becomes our thing, okay? Or it probably actually is going to look a little bit more like this, and these 3 points are going to probably be our support vectors, okay? And the problem is that this guy, this point, is messing us up, right? Is influencing our boundary a little bit too much. Okay, and so we can take care of this using a soft margin. Okay, so before we said we defined the margin as, you know, the distance from the nearest point to the boundary. Okay, and with a soft margin, we're going to just kind of multiply that. You know, the way we optimized it was using a constraint called a Lagrange multiplier, and we said, you know, and I skipped over all of the math there, but basically in that problem during the optimization we said that it's subject to this constraint and the distance has to be a certain amount. Okay, we're going to change that and say, well, you know what, we're still going to optimize this, but it doesn't have to be that exact amount. Okay, and so and try to fix this using a soft margin. Okay, and then the idea behind a soft margin is that we can allow points to be within the margin. Okay, so and this is when you know, there's a value called xi. Okay, I don't know how to write. how do you write the Greek xi in? Yeah, that's when it's that's the capital, right? The capital xi looks like this, but well, whatever. Okay, it looks something like this. All right, the lowercase. Okay, whatever. Okay, I'll just say xi is between 0 and 1. Okay, or we can even allow xi to we can even allow points to be on the wrong side of the margin, or to be on the wrong side of the boundary. Okay, and that's for xi greater than 1. Okay. Okay, and then and so when that happens, basically you can have additional additional points taken into account in determining the boundary. Okay, and then there's another parameter. Okay, another parameter c can be used to kind of decide how how much weight each point has. Okay. And then so, you know, lower values of c will allow the boundary to be influenced by more points. And okay, so this is all kind of just this high-level conceptual stuff. We're not getting really into the nitty-gritty here, but that's okay. Okay. And then there might be some cases where we want to actually where a linear boundary no longer works. Okay. So, what do we do? All right, so if we have, let's say I have something like this, and I'm trying to separate our cases, what do we do? Okay, so we might be faced with a problem where a linear boundary doesn't work. Okay, or another example is we can have all the points here, and then all of these points out here, right? And if we had to draw, if we were allowed to draw curved lines, we could probably do something. Okay, so this is where we bring in something called a kernel. Okay, and in this case, a kernel is a transformation. Okay. Kernel transforms our data. Okay. So, sometimes into a higher dimension or something where we can then separate things out, okay? Where a, linear boundary could work. So for example, we could have a transformation here where and now, I don't know what we could have a plane that cuts through this and separates the blue from the black. Okay, so now what's that? The same, maybe. Okay, and so the kernel is this kernel function that that we apply to a point. Okay, this is the transformation. Or we'll say this is the transformation, okay? And we actually, the amazing thing is we actually don't even need to know what the exact transformation is, okay? All we have to do is know the inner product of after the transformations have happened, okay? So we actually do not even need to know transformation. Okay, we can we just need the the resulting inner product after the transformation, okay? So what this results in is, okay, so I'm run out of space, and let me just slide everything up. Is that, you know, we apply the kernel to a pair of points, 2 points, xn and xm. Okay, so this is a function applied to 2 points. And what it just returns is the resulting inner product of the transformations. Okay, so some transformation and the resulting inner product. This is our kernel function. Okay, so it's just we don't need to know the actual transformation itself. We just need to know the resulting inner product there. And okay, and so this sounds all complicated and everything, but really, you know, we're just going to kind of apply these kind of not magic functions, but you know, we have a few things that work just right off the bat. The linear one is the one that we've been using. Okay, so you know, our linear kernel. This is the one we've been using. Is just the inner product between the 2 points. Okay, so you know, no transformation has happened. Okay, but then you can have a Gaussian kernel. All right, and what we're going to do here is we take our 2 points and we take, you know, kind of the difference between them, and then we have the inner product here, and then we exponentiate this, right? But we multiply by we're going to multiply that by some value gamma. Okay. But this is called the Gaussian kernel because if you look at the way our Gaussian distribution is set up, there's, you know, a term very similar to this that appears in there in the Gaussian distribution. Okay, or a polynomial kernel. Okay, and so what happens? So with all of these things is we're just taking the results, you know, after some transformation, okay, and the inner product there, and when we use these to determine our decision boundary, this allows us to have decision boundaries that are no longer straight lines. Okay, so. Okay. And then there's also kind of these additional parameters that allow us to adjust how much influence each data point has, right? So the C parameter still exists to tell us how much it kind of controls which influence each observation in the training data has. Okay, so I'm going to so we'll try out just a little bit in R and see how this goes. Well, we'll see how far we can get. Okay, so let's. I'm using this this code from a tutorial that was online. Okay, so we're going to start off with 150. This will be a number of data points. Okay, and then I'll say in 2 dimensions. Okay, and then we'll just we'll start off with sigma 1, and then the mean of our positive will be 0, and the mean of our negative we're going to set to be 3, and the number of positives will be n over 2, and then number of negatives, well, I guess I should round n over 2, okay, and just in case it's, and then n will be n minus, number of negatives will be, so we got a positive class and we have a negative class, right? Okay, so then I'm going to just create a matrix, and I'm going to generate some R normal examples. Excuse me. And what I want is, I've got 2 dimensions, so I'm going to just throw. I'm going to get 300 of these values, okay? And standard deviations will be sigma. Okay, so all I'm doing is I'm just generating 300 random values, and then I'm arranging them into 150 rows, 2 columns. Okay, and then I'm going to do, whoops, I haven't run any of this yet. Okay, and then I do the exact same thing over here, except for x negative, and I guess number of negatives, and we want the mean negative here. Okay, and then we'll. Yes.
Should the second entry in the matrix be n negative instead of n positive?
Did I mess something up?
Inside the bracket, the second term should be n negative.
Oh, yeah. You're right. Thank you. Okay, and then we're going to just throw them all into one matrix. Okay? All right, so I can just, if I look at, I've got, 150 values. I'm sorry, yeah. So, and then, if I just look at the head of this, here the ones, these are centered around the mean positive, which is 0, and then if I look at the tail of x, they're centered around 3, right? And then we can kind of and our labels, okay, basically the first 75 are going to be positive, and then the last 75 are going to be negative, okay? So I'm going to just, I'm going to repeat positive 1 75 times, and then I'm going to repeat negative 1 the remaining number of times, and we're going to just throw this into a column vector here, right? So this is these are my labels here, okay? And then I'm just going to plot x, and then the colors will be basically we'll say if y is positive, color at 1, otherwise color at number 2, right? So I do this, and this is my my plot here. So I've got, you know, this area where it is centered around 3, this area where it's centered around 0, okay? Because I just said the mean in the x and the x and y direction here. Okay, so this is what I've got. Okay, and then so we're going to create a training data set. I'm going to just take 80% of our data. That seems to be like our, and then I'm going to just sample, I guess, let me set seed 1 here. Sample n train. I guess I should have set seed before I generated my data also. So set seed there, okay, and then sample right there, okay, and then we'll pull x train, and then we'll pull the same thing for x test. It'll be everything x minus the training ones. And then we'll do y train, the y with the indices of the ones we've pulled, and then y test will be the ones where we did not. Okay. So far, everything okay? Okay, and then we're going to just create a vector that says is train is. We're going to repeat 0 n times. Okay, and then we're going to just. This is a training one. We'll do t index for those. We're going to set this equal to 1. Okay, so this just tells us which ones are training cases. Okay. All right, and then so I'll just plot this. Our colors will be if else. If y is greater than 0, then we'll use 1 versus black versus red. And then as far as the plotting character, we'll do if else is train. If it's a training one, we'll use plotting character 1. Otherwise, we'll use plotting character 2. Okay? So you can kind of see. I don't know if you can see. Okay. So the training ones are the circles, and then if they're the test cases, then they're triangles. Okay, so that's all we've done so far. Okay, and then now we have to load up this library called KernLab. Oh, shoot, I forgot to install it over here. KernLab. Okay. Okay, so we'll load that up, okay? And then we're going to use SVP. We're going to store this as kind of the results here, and the command we're going to use is ksvm for our support vector machine thing, okay? And we're going to take in our training X, our training Y, and then for here we're going to use type C SVC, okay? Kernel will be, so we can look at all of the what all of these things mean. Our kernel is the vanilla dot kernel, and so these are all of the options I'm running here. Okay, so I'm going to just run this, okay, and then it's done here, all right? And then so if I just say, okay, print out what SVP does, okay? It says support vector machine object of class KSVM. The type, it's a classification this. Our cost parameter is 100. We're using the linear, the vanilla kernel, the kind of the most basic one. The number of support objects is 3, so it used ended up using 3 values here, and this is what it says, okay? And so as far as our training data goes, it didn't make any mistakes here, okay? You can we can look up KSVM and see, you know, some of the options that this has, the different kernel types that we have for classification, and you know, we have all of these different things. We've kind of been using just regular old classification, and then again our kernels you can kind of see we've got all of these different things, and so you know, the vanilla dot kernel is, it's talking about, you know, the linear kernel, it's just you're doing the inner dot product, the quote vanilla dot product for our kernel there, okay? Whereas all of these other things we can, yeah, whatever, you know, the polynomial dot product and things like that. Okay, and then so we can also plot this, okay? I can say plot the result that we got, SVP, and our data, using X data, the training thing here, okay? And it looks all fancy, but and so it shows these were the I guess the 3 support vectors that it selected, okay, to create our boundary. Let me show. Let me see if I can plot the other thing. Attributes of SVP. Oops. Okay, hang on. So these are the support vectors that it ended up selecting. Okay, we can see which of the points were the support vectors. Okay, points 81, 85, and 119, and I guess this is kind of some of these values here. Okay, I guess we'll end here for now. I'll post all of these links up on CCLE, and you guys can take a look. Okay.